Today, I will be talking to you about geometry processing research in Python. It's going to be a little bit more chaotic because I'm going to actually execute code live in the session, which is something I have never done because you should never do this. Never execute code in your talk. But this is supposed to be sort of a tutorial, so that's what we're going for here. So what will you learn today? You will not really learn Python today. I assume you already know a little bit of Python, but I will teach you a few Python best practices that you should be using in geometry processing. You will learn the basis of starting your research project in Python using NumPy and SciPy. You will learn how to use some basic functionality of the GPy toolbox geometry processing library. And then you will learn how to visualize, for prototyping purposes, your geometry using Polyscope. And all of this is sort of, the goal for this is to teach you to do basic geometry processing research. If you have sort of just started your first geometry processing research and your advisor wants you to do something, then this is the course for you to understand what your advisor even wants of you. So I'll make this more explicit. Who is this for? Maybe you're new to the field. Maybe you are old to the field, but new to research with Python specifically. Or maybe you have used other visualization or geometry processing libraries in Python before, and you're just sort of you're new to GPy Toolbox and Polyscope. And you want to know how to quickly get a few basic geometry processing things done in Python. I'm going to assume you already know some basic Python and that you're familiar with your computer's terminal environment. So as long as you know the last two, I think you're good to go. So there are detailed course notes that come with this SGP grad school course. And I want to say this is sort of my main contribution here, is that there are these course notes. And they are, I want to say, sort of a thorough introduction to your first few steps of geometry processing research in Python. And what we're going to do here is I'm going to walk you through a few of those tutorials. You can follow along, or you can just write down this link and go to them later if you want an introduction to Python. Always feel free to email me. Both me and the authors of the other libraries that I mentioned earlier are pretty active and are very happy to help you if you have questions or if you find a bug in a library or something. So the rest of this will be live. Not only will it be live, I'm encouraging you to interrupt me in case you have a question about something in particular. Just interrupt me. It'll be fine. I don't think we're going to get through the whole sort of GitHub repository that I put down there anyway. So don't worry about the time. Just interrupt me if you have a question.
I'll interrupt you.
Cool. Interrupt me. Who?
Font size larger?
Can I? Can I? Let's find out. Who knows how the terminal works on Mac?
Bigger is there.
Bigger. Perfect. Be bigger. Bigger. Good enough? Thank you. That overlaps the other window. OK, cool. OK, where was I? So most computers will come with some form of Python pre-installed. I think even Windows these days comes with some form of Python pre-installed. So you don't need to even install anything to get started with your geometry processing Python research. What you should do, however, and what I always do for every research project you do, create your own virtual environment. Before you do anything, create your own virtual environment so you can control the versions of all the packages you will be using. Python is wonderful, and its whole package ecosystem is wonderful and allows you very easily to pull in libraries. A downside of this is that it is also extremely easy to get into sort of library hell, where you have a different version than somebody else, and you have incompatible versions of things. It's best, what I do for every project I do, I start a new virtual environment. I would say there are two popular ways to do this. They are Venv and Conda. I've used Conda my whole life, but I've recently been converted to Venv. The good thing about Venv is it just comes with your Python. Here is how on my Mac I create a new Venv environment. So I did it. Once I created it, I can activate it like this. It works slightly differently in Windows. There's a different activation script. You're going to find this on the GitHub. And that's all you need to do. This is for my current project, GP. If I want to do another project, I would write deactivate and then activate the environment for that other project. Now I have sort of a clean Python environment that isn't polluted by the packages that I've used in my other projects. So let's start by installing some of the packages that we're going to use today. They are, as I mentioned earlier, they are NumPy, they are SciPy, they are GPy Toolbox, and they are Polyscope. I highly recommend always specify the versions of the packages you're installing. Just the most important thing in science is reproducibility. If your code isn't reproducible, then it was just sort of playing around. So one part of making your code more reproducible is to write down the exact package versions of everything you used. And you do that in pip by doing this equal equal and then the exact version of the thing you're installing. So now we installed Python, we installed our packages. There are two ways with which I normally execute Python code. The first is you can use the interactive shell. You can say print hi. And that's how the interactive shell works. Personally, I think for anything that's more than 2 or 3 lines, I like having a file that is sort of a working script. This is why I have the text editor on the right open. I have this file here called working script that is now open. You're going to complain about the font size. Let's see how to increase the font size in Sublime. How to increase the font size in Sublime? Where? Command. Thank you. Yeah, thank you. OK, wonderful. We increase the font size. I like having this sort of working script here. So that way I will write here, print, ooh, that is very large. Hi 2, and execute my working script with Python. I find that better than the interactive console. I like it better. Cool, so we started Python. We booted our interactive console. We are ready to do our first little bit of research. If you ever look into the GitHub repository, it's sort of structured into these exercises. So that was exercise 0. Now we're going to go on to exercise 1. I'm going to open the script for this. Here we go. Cool. So first we're going to learn a little bit about NumPy in geometry processing. Some of you might be familiar with MATLAB. And NumPy actually shares many similarities with MATLAB. There are a few important differences, and I want to highlight the most important things you need to know about NumPy here. So the basic data type in NumPy is called array. Maybe there is such a thing as a too large of a font size. So the basic data type is the array. If my array only has one dimension, if it only has a list, then this is like a vector. Execute this. The vector, this is the vector 1, 2. But I can also use this to define matrices. So if I have a sort of 2-dimensional list here, this matrix A, this defines a matrix. And NumPy, by default, uses row major format. So I specify the rows first, and then the columns. This is what the matrix looks like. And once I specify these arrays, I can do a variety of the usual element-wise arithmetic with it. I can add them, I can subtract them, I can multiply them, I can divide them, I can exponentiate them as if they were scalars in normal Python. So here are a few examples. Here I have 2 arrays. Oh, it doesn't automatically line break. OK. You can do all the usual operations, and you can also do them with a scalar. So if I do here a minus 3, it'll subtract 3 from all the elements of the matrix, and so on. That works as if the entire matrix was only composed of scalars. What is slightly different than MATLAB, for example, for the people here who might be used to MATLAB, here the star operator does an element-wise multiplication. In MATLAB, it does a matrix multiplication. If you want to do a matrix multiplication in Python, this works like this with the @ operator. The the star operator by default is an element-wise operator. So this is a matrix vector multiplication in NumPy. And the other thing that works slightly differently than MATLAB is transposes. So if I want to take a transpose of a matrix in NumPy, it is this dot t, and not the dash that you know from MATLAB. Then sort of the last basic linear algebra thing I personally use a lot in NumPy is I take the Frobenius norm of a matrix, or the Euclidean norm of a vector, and you do this with NP linalg norm. You use this, for example, if you decide that a matrix is small, right? They're floating point numbers. You can check for equality with 0, but you can check if the norm of something is small. You would do this with NP linalg norm. OK, that's sort of the most very basic things that we do with matrices in Python. I'd say the first non-trivial things that you want to do with matrix is maybe you want to invert a matrix to solve a linear system. What you should never do, except in rare exceptions, you should never literally invert a matrix. NumPy has a function to literally invert a matrix. You should never do this for a variety of reasons, both numerical and performance. What you should do is you should use a built-in linear solver. So in MATLAB, that would be the backslash operator. In NumPy, it is this np.linalg.solve. This solves the linear system. It does inverse of A times B. You notice with this np.linalg.solve. I think this is all you need to know, sort of a basic matrix arithmetic in Python. There is one little bit that I think you should know, because if you do my type of sort of geometry processing, you will come across this a lot, which is sparse matrices in Python. So the way we wrote down matrices so far as this NP array thing, you specify every entry of the matrix, and if you have a matrix where most elements are 0, and you know that most of them are 0, this is a giant waste of memory. You will waste so much memory for writing down just 0. Very often in geometry processing, you will encounter matrices that we know overwhelmingly most of their entries are 0. For those, it makes sense to only specify the non-zero matrix entries. These are called sparse matrices. I'm going to write down a little thingy. I hope you can see it. Of how we're going to specify them using the SciPy package. So this sort of looks trivial, but for every element of this sparse matrix that is non-zero, we will have a row index, we will have a column index, and we have a value. Together, they form a triplet, and we can do something called a triplet list. And here is an example of how this works in SciPy. So I have my vector of rows, I have my vector of columns, and I have my vector of values. And in SciPy, I assemble something called a CSR matrix. There are a variety of sparse matrices. It's not that important for you to know the differences between them at this point. You assemble them like this. You have this sort of bracket with the values, the rows and the columns. And it works like that. Now, if I was a member of the audience, I would now ask, what happens if I have a duplicate index here? What happens if I have another entry that's 2, 2 here? Does someone already know? This is not a bug. You're allowed to do this. Yes? It'll add them together. Thank you very much. So this is very flexible. And if you have a sparse matrix, never use NumPy array. Use one of those SciPy sparse matrix things. You solve them the same way if you have to solve a linear system. Again, do not invert them explicitly. That is a bad idea. Never explicitly invert a sparse matrix. There is another one of these solvers. For sparse matrices, there is sparse linalg SP solve. And works exactly the same as it did for dense matrices. Another last trick I want to teach you about sparse matrices is that solving a linear system with a sparse matrix is actually quite expensive. But if you want to solve a linear system with the same matrix and different right-hand sides many times, you can save yourself a lot of time by doing a pre-computation. So most of the work that the computer needs to do in order to solve this system inverse of A times B is in sort of pre-computing for the matrix A. And then if I want to solve another system that's inverse of A times C or inverse of A times D, I'm able to reuse this work and do this efficiently. And in SciPy, this works like this, where I use a solver that has this decomposition ability, SPLU, and I get back this pre-comp object. And then I can solve a variety of linear systems with different right-hand sides with this sort of same decomposition that I've done. In many geometry processing algorithms, you will see this as a feature. If a geometry processing algorithm involves, for example, the solution of many linear systems, but it's always the same matrix, then they will put it like in their feature list that like you can offload work into pre-computation, and then they don't need to report it every time they run the algorithm. OK, this is all I'm going to say about linear algebra for now. If you ever do, for example, machine learning research, you will need to interface with maybe Torch or JAX. There are instructions for this in the tutorial, but I'm not going to go through them now. I'm going to pause a little to see if anybody has linear algebra questions. Otherwise, we'll move on to geometry. OK, let's move on to geometry. Great, OK. We've done linear algebra. Let's move on to our first surface. So the standard discrete surface representation that we use in GPy Toolbox, usually for most things, is the triangle mesh for two-dimensional surfaces or the polyline for one-dimensional lines. And a triangle mesh is just a surface consisting of piecewise triangles, and a polyline is a line consisting of piecewise lines. And the format with which we usually work is called the vertex list face list. The vertex list is a matrix V where every row is a vertex in the triangle mesh, and we have as many rows as there are vertices. I'll give you an example of a vertex list. So here I'm going to set up a vertex list. It has 3 rows, and I'm going to also draw on the blackboard for this. There is here 0, 0, 1, 0, and 0, 1. Those are the 3 vertices that I've specified. That is my vertex list. And after the vertex list comes the face list. The face list specifies which of these vertices belong to which triangles. The face list, again, has many rows, 1 for each triangle. Here is an example of a very trivial face list with only 1 triangle. Oh, sorry, I'm doing open here repeatedly. With only 1 triangle, 0, 1, 2. So here I specified that this triangle contains those 3 vertices. This references the rows in the vertex list, the 0th one, the first one, and the second one. Here's a very quick polyscope visualization of our first one triangle mesh. I will teach you how to use polyscope soon, but I wanted to go over meshes first. All right, you will see that this is the triangle that I drew on the blackboard. The vertex 0, 1, and 2. Now, this is a very boring face list. It only has 1 triangle. We can sort of trivially add a second triangle to it. In this case, I've used the vertices 2. I've added a third vertex here. And I've used the vertices 2, 1, and 3 to add a second triangle. And this is how that looks like. 2 triangles. You can, in polyscope, if you click here, you can see the edges, so you can see all the triangles individually. And now we have 2. Now we have 2 triangles in our triangle mesh. Now, I know that the sort of triangle content is riveting, but it becomes unwieldy to specify your triangle meshes if you have to sort of write down the coordinates of every vertex and the topology of every triangle individually. So what we usually do is we write them down in files. A classic way to share geometry in files is something called the OBJ mesh. And they're written in files. So here in this directory, data penguin, I saved the penguin mesh in GPy toolbox. You're going to read this with read mesh. It automatically reads it out into a vertex list and a face list. To be honest, this is the GPy toolbox function I use most. Because at the beginning of every single script or whatever, you need to read in a mesh. This goes very easily like this. Penguin. This penguin is going to guide you throughout the whole tutorial here. The last way with which you're going to generate geometry in GPy toolbox is there are certain surfaces which are described entirely mathematically, and we can sort of generate them using parameters. A perfect example of that is the sphere. You don't need to save the mesh of a sphere. You can generate a sphere of arbitrary resolution of the triangulation that is called an icosphere, because on its lowest resolution it's an icosahedron, using a GPy toolbox function called icosphere. This is what that looks like. And the number here determines the resolution. So if you go higher, you'll have a higher resolution sphere. Great. There are a variety of these in GPy toolbox. It'll generate a square for you. It'll generate a cube for you. It'll generate a circle for you. For sort of those regular, I think even a torus. We have a torus too. For those regular meshes, this is all you need. Yeah. One last thing I want to mention at this point is that if you ever have, if you're ever unsure of what any of the GPy toolbox functions do, for example, this one, you can open your Python console and go help. Go help, and then the name of a function, and then it brings up the documentation. No, I have to do this. It brings the documentation, and it tells you exactly what parameters it has, what it returns, and so on. OK. So far for how to generate simple meshes. We learned how to generate simple meshes. Now, how do we visualize meshes?
Can I ask a question?
Sure, yeah.
Hold on a second. I'll give you the microphone. Just a very, because it's in the recording.
So the surface meshes in Polyscope, are they triangle meshes, or can you have mixed meshes with all kinds of faces?
So it depends. I want to say that GPy Toolbox is generally. I want to distinguish here between GPy Toolbox and Polyscope. In Polyscope, you can plot triangle meshes. You can plot. I think he has quad meshes now, and you can plot polylines, not in the same structure. In GPy Toolbox, it depends on the algorithm you call. Some of them work on tet meshes. Some of them work on triangle meshes. But I want to say for the starting student, you will probably stick to polylines or to triangle meshes, whether you're dealing with lines or with surfaces. The majority of functions work either on polylines or on triangle meshes, and not on mixed versions of them.
Could I ask a follow-up question to that?
Sure.
Thanks. So does GPy Toolbox, it doesn't have its own visualizer right now, like it relies on the Polyscope visualizer?
I don't think it will ever have a visualizer. Polyscope is so good that you should use Polyscope.
OK, OK.
There's no reason, right? It exists and it's good. OK, let's go on to a basic Polyscope introduction now. Before you do anything in Polyscope, what you need to do is you need to initialize it. Before you call any other Polyscope functions, it has to start with ps init. After Polyscope has been initialized, you add to the Polyscope scene, you add structures to it, and then on these structures you can add quantities. So for example, the penguin from earlier, that would be a structure. And if it's a surface, we add it with the function register surface mesh. And then after we've added structures to things, we start the Polyscope window with calling ps show. That is sort of the basic Polyscope loop. You init, you add structures, and then you show. How the penguin works. There is an important difference between the people here who might be used to doing geometry processing in MATLAB and the people who do who want to switch to Polyscope. Polyscope blocks your console while you execute it. So in MATLAB, if you call your visualization, you can continue to put in console commands. Polyscope does not. As soon as you call show, it blocks the console, and you have to exit the window to sort of return control back to the console. Yes?
If you're interested, I had a monkey patch that I have implemented a monkey patch that overrides show and all other necessary things to invoke into the event loop of Polyscope to be still able to execute Jupyter Notebook commands.
Oh, wonderful.
So if you're interested in just
message me after the fact. I'll add it to the GitHub repository for this. There's a note warning you not warning you about this, but I'll add a link to your monkey patch. Thank you. Yeah. You can add multiple structures. You do this by giving them different names. It's very important that you give them different names. So here I have one structure that's a penguin and one structure that's a wingnut. And if I now open it, indeed, there'll be two different shapes here. And I can enable and disable them at will. If you give something the same shape, the same name, it'll override the last one you added. So be sure to always give them different names. By default, all the surfaces you've entered are shown. As you can see in the GUI, I can decide to enable them or disable them manually, or you can also issue a little bit wider, I guess. You can also explicitly decide whether you want the surface to be enabled or not once you show it. Otherwise, everything is plotted at once, and you can change this later. If you change your mind, you can set it from false, and you can later set it be set enabled equals true. Let me delete this line so you can see something that starts with only one surface showing. Yeah, so here the wingnut starts disabled, but I can enable it later by hand if I want to. OK, great. So far for surfaces. So surfaces are probably the things with which somebody who's new to geometry processing research interacts most, but there are a variety of other things you can display in Polyscope. The most simple next one after the surface is a point cloud. The surface has the vertices and the triangles connected them. If you only have the vertices, this is called a point cloud. And this is added in Polyscope with register point cloud. So here I'm reading in the same penguin, but I'm only passing in the vertices. I'm not passing in triangle information. And it will display only the vertices as a point cloud. And beyond the point cloud, I mentioned polylines that are piecewise lines. Those you do in Polyscope with register curve network. I like to call them polylines, but Polyscope calls them curve networks. They work exactly the same, but here instead of specifying vertices and faces, you specify vertices and edges. And it works just like that. Cool. Now, surfaces are nice and all, but we're here to do math, right? In order to do math, we define functions on surfaces. Polyscope is a great tool for plotting functions on surfaces. And this is done by adding quantities to the surfaces. So if my function is a scalar function, a map from the surface to R, we can display it by adding a scalar quantity. Here my function is just the y coordinate of the surface. So for each vertex, so for each row in my vertex list V, I have one scalar. And that scalar is per vertex y coordinate. And then I add it to my surface structure with add scalar quantity. That is this array. And then I set it to be enabled equals true. Because by default, Polyscope does not plot these. See what that looks like? Cool. It plotted the function, this y coordinate, as this color gradient. Where's my mouse? In Polyscope, you can easily plot both per vertex functions, which are one value per vertex, and per face functions that are one value per face. And Polyscope has this defined on property to the add scalar quantity function to do this. So here, what I'm doing here is I'm spawning a sphere with the same sphere command as before. Then I have one function that is the y-coordinates on the vertices. And one function is the y-coordinate on the faces. To compute this, I average just the y-coordinates of all the vertices in the face. And then I have two different plot commands, one defined on vertices and one defined on faces. Here's what that looks like. Here is the one, you see the one on top that is defined on vertices, and here's what it looks like when it's defined on faces. Cool. This is sort of these are the basics you need to do to display things in Polyscope. But I don't know about you. One of the reasons I'm in geometry processing and computer graphics in general is to let a little bit of my sort of artistic nature shine. So the next section is to show you some things to make your Polyscope plots look a little bit nicer. I was wondering whether I should do this or I should focus on more important things. But I think actually it's important to make your surfaces look nice. Otherwise, you're going to be sad while you do work. So the first thing that I like to do to sort of improve my visual communication and to make my stuff look nicer is to use different color maps. The plots you saw earlier used something called the Viridis color map. I hope I'm pronouncing that correctly. But Polyscope has many other color maps beyond just that. This is a Red's color map. Pasting this in the correct file. No, I'm not. So instead of this Viridis color map, this is the Red's color map, plots things from white to red. And in fact, if you go into this little GUI menu, you can adjust to other color maps that are pre-installed. There are lots of nice pre-installed color maps in Polyscope, but if you're me, you want to take your creativity to the full potential by using your own personal custom color maps. Personally, I am a big fan of Cynthia Brewer's Color Brewer. These are all the color maps you will ever need in your life. If you go to colorbrewer2.org, there's a color map for every situation. Do I need one that's sequential, diverging, qualitative? How many does it need? Oh, I want it to be colorblind safe, and so on. That only works up to a certain number. So I like to go to colorbrewer.org and download a color map, and then load that color map into Polyscope. And you can do this with this function. Load color map. If you have this image that you can download, for example, from colorbrewer.org, you can load your own custom color map. And now, if you plot this, beautiful. I love Color Brewer. It's great. You see that your color map has been added to the other color maps here. You can use it to quite some effect. For example, here's a thing I like to do when I write research papers. I will try to use, for my own results, I will always use one color map. For previous work's result, I will give them their own color map. So it's sort of imprints in the reader whenever they see a certain color map, oh, this is this paper's contribution. And whenever they see another color map, it's like, oh, this is the previous work. And maybe another one for the ground truth. Think about which color maps you use in your visualizations. Another thing which you might have noticed in the Penguin earlier is that all the triangles were visible. Let me maybe run this again so you can see it. If we zoom in a little, you can see the different triangles here. This might not be, artistically desirable to you. The reason this works like that is because when Polyscope computes lighting, it uses the normal of the shape, and it's made out of piecewise triangles. So whenever there's a triangle, there's going to be a constant normal, and you can see sort of the normals change along triangles. If you don't want this, if you want to give your shape a smooth appearance, you can do that in Polyscope by telling the shape to be smooth. In fact, I have this. It's more clearly visible in the sphere. So if you look at the sphere here, you can clearly see where the triangles are based on the normals changing. If you don't want this, if you want a smooth appearance to your surface, Polyscope has this argument, smooth shade equal true, that you can set. If you do that, here's the sphere, it'll appear smooth. Now the sphere is very low poly, so in fact, if you look at the contour, you can still see the triangles. But for the penguin, this is almost eliminate a triangle. It looks like a completely smooth surface now. I usually use this because it makes visualization look nicer, unless there is I specifically want to emphasize the normals in some way. Now the last thing, if you're not plotting a function, if you're only plotting sort of the geometry of your surface, you can try to make it look even nicer by using different materials. That in Polyscope works by using material, for example, ceramic. The repository will have a list of built-in materials that I support. This is not the fancy BRDF model that you heard before noon. This is those sort of simple OpenGL hacks, but they look surprisingly good for sort of this prototyping environment. This is what a ceramic penguin looks like. OK, I hope you've learned everything you ever want to know about visualizing geometry. I will stop a little, and then I will talk a little bit about how we compute basic properties of surfaces, basic geometric properties of surfaces. Great. So here's a basic fact about triangle meshes, at least nice ones. Every triangle in a triangle mesh is adjacent to some other triangle, except at the boundary, where the triangle is adjacent to nothing. The edges that have only one adjacent triangle form something called the boundary loop, and the vertices on this boundary loop are the boundary vertices. And you can very quickly get a list of all boundary vertices from GPy Toolbox using the function boundary vertices. So here I cut some holes into the penguin, but I don't know. This is instructional. And the vertices it gave me back, I plotted as a point cloud. There are these yellow vertices. That's you get all the boundary vertices in GPy Toolbox. Now, you might not want just all the boundary vertices in an unordered list like that. You can saw the penguin had two different boundary components that were not connected to each other. You might want separate lists of all the boundary vertices so you know which one is in which boundary component. And in GPy Toolbox, that is called boundary loop. That will give you back a list of all the boundary components in an oriented loop. If we run this script now, you can see this boundary has two components, so this list has two elements. And if we look at so you see the first one I register as one point cloud, and the other one I register as another point cloud. And so here there are two different point clouds, two different colors. Sometimes you need this, for example, because you only want to do something on the largest boundary component. For example, you're doing parameterization, you only want to fix the largest boundary component. So for this case, you would use boundary loop, otherwise you would just use boundary vertices. Another thing we care about might be the normals. We talked a little bit about the normals of a triangle mesh when we talked about shading. But how do you compute the normals if you just want to use them in a normal geometry processing application? We're going to compute something. In GPy Toolbox, this works with the normals function. So here is the icosphere. I'm doing per face normals. This means one normal per face. Literally for every triangle, we're computing the normal vertex. And it returns to me an array that each row of that array is the normal that corresponds to that triangle in that triangle face list. Now in Polyscope, I can plot not just scalar quantities like the functions we've plotted until now. I can also plot vector quantities here with add vector quantities. Pretend like it's defined on faces. Plot it like this. And here I have the little normal vector plotted for every face. If you want a per vertex normal, for example, because you want to do the smooth shading, your homework is implementing the smooth shading from Polyscope, GPy Toolbox will also give you a per vertex normal function. And well, the per face normal function is called per face normal. The per vertex normal function is called per vertex normals. And you execute it like this. And now you can see the normals will be on vertices. Cool. The last geometric quantity which I want to introduce here, which I think is important to know, is the triangle area. We all use the triangle area for a variety of things. We will use it later to compute, for example, finite element matrices. In GPy Toolbox, there is a function called double area, which computes double the triangle area. So I do 0.5 times the double area to compute the triangle area. This is for historic reasons that you don't need to know. But anyway, double area computes the area of each triangle, and I plot it using defined on faces. These are what the areas of each triangle look like. When I prepared this, I saw this, and I'm like, when I drew the penguin mesh, you see, I slipped a little, so this vertex is to the left of all the other vertices, which makes it a little bit ugly here. Things you can find out if you use the GPy Toolbox area function. Okay. So much for basic properties of surfaces. I will pause a little again to give you a chance to ask a question if you want before we will move on to randomness. Okay, so for many applications in geometry processing, we want to incorporate some element of randomness. Maybe you want a random initialization for an algorithm. Maybe you want to just select places to do something without being biased in any way. And I will now show you how you should do randomness in GPy Toolbox, but really how you should do randomness in all of your scientific research. So I will start by telling you what not to do. GPy Toolbox has a function to randomly sample points on meshes called random points on mesh. So here I load my penguin, and I want to sample 300 points on this penguin. Let's do that. Looks fine. It sampled random points. It sampled them with a uniform distribution. It sampled 300 random points on the surface. And I'm going to run it again. Notice any difference. They're different points. They are not the same points. Which you might say is that's what it's supposed to be, right? It's random. Of course they're different points. They're not always the same points. Well, remember that you are here to do science, right? So if you generate a result using randomness, and then you post your code online, and somebody else runs your code, they will get a different result from you. So when you write scientific code, what you want to do is you want to have randomness, but in a way that is reproducible. And the way to do this in NumPy, which GPy Toolbox adopts, is to have a seed, use the seed to generate a random engine, and then pass that random engine around in your functions that generate randomness. That way you can use randomness, but in a way that is reproducible. Now I'm going to quickly demonstrate how that works here. And this is sort of a smaller scale example. This is in NumPy how you generate a random number. You use this RNG that says default RNG will generate 2 random numbers. Again, if I run it a second time, I'll generate 2 random numbers, 2 different random numbers. Because in NumPy, if you call default RNG, what it usually does is it takes randomness from some sort of secure source in your operating system. Usually your hardware, there's some part of your hardware that can generate random numbers. And this is good, for example, I don't know, if you're generating cryptographic keys, right? You want it to be completely unpredictable what randomness comes next. But it's bad for geometry processing. For geometry processing, in the scientific context, we want reproducible randomness. So what we will do is we will seed this random number generator. I have some sort of integer. I seed it. I call this np random default RNG with a seed. Now when I call it twice, it gives the same random number twice. Great. This exact same context applies to, this exact same sort of setting applies to GPy Toolbox. We also take NumPy RNGs that we can seed. So if I now generate random samples on my mesh with my seed, and I do it again, it's the exact same point cloud. If you only take one thing away from this talk, nothing about Python, nothing about GPy Toolbox or Polyscope, if you have any randomness in your scientific code, make sure that you seed it and that it's entirely reproducible when you run it multiple times. Cool. Nobody any questions? We'll move on to our next topic, which is a finite element matrices. So partial differential equations and their operators are the bread and butter of the sort of geometry processing research that I personally do. In fact, for SGP 3 years ago or 2 years ago, I wrote a theory course about the theory of finite elements in geometry processing, which I recommend you read because this will teach you nothing about finite element matrices. I will teach you a very short intro into how to compute, how to get finite element matrices in the context of GPy Toolbox. And we will talk about two finite element matrices, the Laplacian and the mass matrix. You might know the Laplacian from calculus class, sort of, you know. This is the Laplacian, how we know it from calculus class. I like to write it like this. This is the divergence of the gradient of u, because on surfaces, coordinates are much more difficult, so we rewrite them using operators like the divergence and the gradient that are easier. And this is the Laplacian that you might know from your calculus class. This is not how we think about them in finite elements. In finite elements, we think about them as sort of, the Laplacian as sort of operator. So here, the Laplacian takes a function and outputs a function. The way I want you to think about this so that the finite element matrices will make sense, wipe those triangles here. I want you to think of sort of an operator that takes a function u and that takes a function v and that returns this sort of integral over the surface. This is how the Laplacian will work for us. And the reason we do this is that you saw when we plotted functions earlier, for us in the GPy Toolbox context, a function is something that has one value per vertex. And so this operator that will take in a vector with one value per vertex and a vector with one value per vertex is just a matrix. So all of these finite element operators are just matrices. The Laplacian in GPy Toolbox, the matrix Laplacian, is computed very simply with this cotangent Laplacian. And that returns the sparse matrix that is this operator. So if I multiply a function to its left and I multiply a function to its right, it will have computed this equation. Let's very quickly test this. We know that the Laplacian of a constant function is 0. So if I take a constant function here and I multiply it like that, that should be 0. Close enough. 4e minus 14. That's 0. The second finite element matrix that you will use, I think, very quickly if you do geometry processing research is the mass matrix. The mass matrix does the following. So it just computes the basic integral of something over a surface. And we get the mass matrix in GPy Toolbox using the function mass matrix. How can we check out this mass matrix? Well, we know that the area of a sphere, we know what the area of a sphere is. What is the area of a sphere? 4 pi. Yes? Yes. Thank you. Let's try to use the mass matrix to compute the area of a sphere. Sorry, I was a little bit quick here. Again, I have a constant function, and I compute this. I use this mass matrix to compute this integral over the sphere. Great. Close enough. Let's use this actually for an application. One of the things the first things I ever did with the Laplacian in geometry processing was denoising a noisy surface in a process called surface fairing. So why would you do this? Here's an example of a noisy surface. I've taken the penguin from earlier and added noise to it. You can imagine that it comes, for example, from a measuring error or so on. For some reason, you have a noisy surface, a noisy penguin. And this is a famous paper by de Bruyn et al. That says you can denoise it by solving sort of a one step of a heat equation. It'd be like U1 equals U0 plus T Laplace of U1. Yeah. And if you translate this to the language of integrals and matrices like we have here, we have here our cotangent matrix, we have here our mass matrix, we have here this T step, and it becomes one linear system that we solve at the end. Correct, M plus TL U1 is M U0. This is one step of this surface fairing algorithm, and it will smooth our noisy penguin to make it a little bit smoother. Cool. So far for finite element matrices, I think this is all you need to know about finite element matrices. I will end this, unless there are any questions, by showing you how to solve a basic optimization problem with GPy Toolbox. So many research problems in geometry processing can be boiled down to solving an extremely simple optimization problem that goes like this. Don't you have ever seen this before? This is an extremely simple quadratic programming problem with a simple linear constraint. Here, AU equals B is an obvious matrix constraint, and this here means that the entries K of the vector U are equal to Y. And this looks easy, and but so many problems that you will solve in geometry processing are just versions of taking some sort of mathematical equation and reducing it to this exact optimization problem. This comes up so often that we have a special function for this in GPy Toolbox that we call min_quad with fixed. That's adapted from an earlier GP Toolbox function that did the same thing. Here is an example with no constraints at all. So we just have this function where we have here u squared times 4 plus 7. Yeah. The ones of you that know that know by heart how to find the minimum of a quadratic function can check my math here. So you can use it to optimize a simple quadratic function. You can use it to optimize it for a larger matrix. So here Q is a larger matrix, and C is a larger linear term. It works the same way. Probably important to mention here at this point that this doesn't, I wrote min here. This is wrong. I shouldn't have written min. It's easy to understand away, but it sort of finds critical points of this, right? It'll also, if your function has a maximum, it'll find a maximum. If it has a saddle point, it'll find a saddle point. This is especially relevant for matrices, which can have saddle points. OK, this solves a general quadratic problem. This is not so hard so far. You can do this yourself by just putting this into a linear solver. It becomes more interesting when I add constraints to it. For example, let's say my goal is to find the smoothest function fulfilling some sort of constraint. There's a little bit of a more complicated function for this. So here's what we're doing. We're computing the cotangent Laplacian, the finite element matrix from earlier. This will help us to quantify the smoothness of something. I choose the index that is the head of my penguin, the index that is the foot of my penguin. I put those into my vector k. This is going to be my index vector here. And as the matrix term, I have my cotangent Laplacian from earlier. But now I have this additional constraint. So I want the smoothest function such that the head is fixed to 1 and the foot is fixed to 0. This gives me this. It gives me a function that's 1 at the head, 0 at the foot, and smooth in between. If you learn a little bit more geometry processing, somebody will tell you sooner or later that you should actually never use the Laplacian if you have pointwise interpolation constraints. What you should be using is the biharmonic energy. So we also have this in GPy Toolbox. We have implemented the biharmonic energy, which is a better choice if you want sort of smooth functions and have isolated constraints. Give us a much nicer result. This is the result you want, where it's 1 at the head, 0 at the foot, and smooth in between. I'll show you one last example of sort of mixing these index constraints with a linear constraint. You can also do that. So let's say instead of wanting the head to be 1 and the foot to be 0, I want my head to be 1, but I also want the entire thing to average to a certain number, the entire function to average to a certain number. I will do this with a linear constraint. Here, this m from earlier computes the integral. So I want the function integrated over the whole surface to integrate to 0, and I want it to be 1 at the head. Give me the following function. This one is symmetric, unlike the earlier thing that I did, right? But you see both the feet have the same value now, and the head is 1. I think this is a good spot to end. I've taught you sort of the most important things that you need to know. You know how to read a mesh. You know how to visualize a mesh. You know how to reproducibly sample random points. You know how to compute finite element matrices. And you know how to solve this simple quadratic optimization problem, which should turn up in all of your research problems. I'll pause here for questions. Who is somebody here asking?
I hope this isn't a silly question, but do you use Polyscope directly to do the renders for your papers?
Yes and no. So most of the time, when I do renderings for my paper, I will want something that is sort of high quality, and I will use Blender for that. And Sylvia, actually, who organizes this grad school, has a great tutorial on how you should do your paper figures in Blender. I think most of the paper figures that I make that end up in the paper are in Blender. But Blender isn't particularly suited, I feel, for sort of doing research, for actively doing research. So let's say I plotted a function. Let's say, I don't know, I want my function to have, I want to see the isolines of the function or something like that, right? This works like that. Oh, this quickly shows me the isolines. In Blender, I would now have to write an isoline script. I would have to re-render it. It would take 15 minutes. I think for actively doing research, you want to be using Polyscope. Get all your paper examples ready. Once they're ready, then write Blender visualization scripts for each of them. and then put the Blender figures in the paper. That is what I do.
A follow-up question then, is there an easy way to save the textures from this in order to export and import into something like Blender?
What do you mean, the textures that are on the thing?
Like the vertex colors.
Not from Polyscope, as far as I know, but it's very easy from GPy Toolbox to do it.
Okay.
It's just so NumPy has a function that is NumPy save or something, and that will allow you to export every result that you have into a NumPy file. And then Blender has a Python console, which has NumPy in it. You can just load it via Blender. That's usually what I do. I do also.
If you're running out of time and you can't load up Blender, there's some nice anti-aliasing built into Polyscope. So remove the ground plane and just up the anti-aliasing, and it looks great.
There is a thing in the actual online tutorial. There is a thing on how to remove the ground plane. Yes, I can remove the ground plane. I can have it none, or I can set it to have shadow if you want a shadow.
Yeah, and now do up the anti-aliasing.
Think my graphics card can handle it? It can. Great, lovely, wonderful. Thanks, Ron.
So I have a question about, I remember last I used Polyscope, there was like some feature to render voxels as well.
Yeah, so there is an entire thing to display tet meshes and to display hex meshes too. There are so many more features on Polyscope. It is, I think, the end-all be-all of sort of prototyping visualization library. You can visualize most geometric structures with it.
I see. Yeah, so last time I used it, it only could handle dense voxels, I believe, not like narrowband voxels. Has that changed?
Well, Ron, correct me if I'm wrong, but it works with general hex meshes these days, right? Polyscope.
I don't use hex meshes.
Oh.
Yes, it does.
Yeah, so I think it does. It works with general use hex meshes.
Okay.
Yeah.
I was wondering, do you have half-edge data structure in GPy Toolbox?
Yes, but in sort of our own way. So you might think of this will not make sense for people who don't know what a half-edge data structure is. But so you might think of a half-edge data structure as lots of things in linked lists, right? So we don't have that, but we have. You can simulate a half-edge data structure purely with matrices with indices in them. So that is something I skipped because it would have been horrible to do live. But if you go to the GitHub repository and you go to exercise 6 that is called edges, half edges, and adjacency, it shows you how half edges work in GPy Toolbox. Every half edge is a unique index. Because every face is a unique index and every vertex within that face has a unique index, every half edge has a unique index given by the face index and the vertex index. And based on that, you can use all of your normal half edge routines. So instead of pointers into linked lists, which you might be used to from sort of classical half edge data structures, we just have indices that are given by the face indices and the vertex indices, and you can use your half edge functions that way. It's useful, for example, to compute adjacencies of faces and stuff like that.
We'll do one last question because we're eating into the break.
What is the difference between GPy Toolbox and libigl?
That's a good question. So libigl is a old, powerful, mighty geometry processing library originally in C++ that now has very strong Python bindings. It is a great choice for geometry processing, and you should use libigl. GPy Toolbox is just a sort of different library that Sylvia and I wrote, which is a different approach where instead of having this large C++ library, we have a Python library where most functions are written in Python and have a sort of unified, simple Python interface. GPy Toolbox does much less than libigl. It is sort of an alternative for libigl for the stuff that it does. Cool. If there are no more questions, I want to give quick acknowledgments. First of all, to Nick Sharp, who made Polyscope. It's great. I love it. Use Polyscope. And to Sylvia, who wrote GPy Toolbox with me. and to Sylvia and Ed, who organized the grad school. Thank you very much.